In this next example now, we have a circular loop. It's made from a flexible conducting wire and it's shrinking. Its radius as a function of time is given by some constant rho, e to the minus beta times t. The loop is perpendicular to a steady uniform magnetic field B. So let's see what we're going to do here. How are we going to work this out? We want to find an expression for the induced EMF in the loop at time t. So let's just do a quick sketch. We have a circular loop. It's got some radius as a function of time, so it's getting smaller. The loop is perpendicular to a field, which means that the plane of the loop is perpendicular to the field and the area vector is parallel to the field. Find an expression for the induced EMF at time t. So we'll write Faraday's law. Induced EMF, induced potential, is minus d phi dt, the magnetic flux with respect to time, equals minus d by dt of B dotted with the area, equals minus d by dt of the magnitude of B times the magnitude of A times the cosine of the angle between them, in this case that's 0, minus d by dt of B times A. Okay, so we're getting started. What is the area of a loop? The area of a loop is pi r squared. What is the r of the loop? That's given by our equation here. So let's square this term, which means we square the r 0 and we square the exponential term. When we square something with an exponent, we multiply the exponents. And now we want to take the time derivative of this. Let's take our constants out front first. So we have minus b times pi times r0 squared times d by dt of e to the minus 2 beta t. So we have to take the derivative of this guy. The derivative of that guy is equal to, we have the thing by itself, e to the minus 2 beta t, times the derivative of what the exponent is. The derivative of minus 2 beta t is minus 2 beta. So let's make this look a little nicer. Minus times minus is plus. We've got the 2, b for magnetic field, beta for that parameter in our exponent. So b times beta times pi times r0 squared, e to the minus 2 beta times t. So there's an expression for the induced potential as a function of time. You can certainly leave it like this, but something that's a little bit neat that you might notice is that this is r squared. So the induced potential is 2 times b times beta times pi times r squared. That's kind of interesting too. What else might we notice? As time goes on, as t goes to infinity, the size of the loop goes to 0. And what does that mean about the magnetic flux? It means eventually there's no flux going to the loop. So that means that eventually our induced potential is 0. So when it gets down to 0 size, there will be no induced field or currents. Okay, let's do at least one more example on this video. Let's take a 20 centimeter square loop of wire. Let's place it in the xy plane with its bottom edge on the x-axis. Okay, let's draw this before we even read anymore. So I'm going to draw the xy plane the usual way. There's x and y. Z would come out of the page. Our square loop lies in this xy plane. So it looks like this. And it says the bottom edge is along the x-axis. What can we say here? Well, let's just leave that for right now. The resistance of the loop is 0.5 ohms. The field is parallel to the z-axis and given by this expression in B. What is the size of the induced current at t equals 0.5 seconds? So the direction of the magnetic field is out of the page. So there's our B. What you might notice in the equation that the size of the magnetic field depends on your vertical position, it depends on y. That gives us a hint that to calculate the magnetic flux, B is changing, so we're going to have to do an integral there to find our B. So we know that induced potential is minus d phi dt. There's our induced potential. So let's find our flux, then we can come back and find our potential. So our flux, magnetic flux, is the integral of B dot dA. So our B is easy, 0.5 y squared t. dA, or why don't even we write this, B times dA times cosine theta. There we go, because that's the usual way. Let's pick a dA. dA means a little bit of area of this loop. For the area I'm going to pick a rectangle that has a length here, which is a little bit in the y direction. It has a width in the x direction, and it has a direction that comes straight out of the face. I could have picked into the face as well, but I'm going to pick out just to make those guys parallel. So that's B times dA times the cosine of 0. So let's fill in what we have so far. That's the integral of B, which is 0.80 y squared times time, times dA, which is length times width, so x times dy, times cosine of 0, which just gives us 1. The limits of the integral are, they're a limit over the range of y, so the width of our loop x, that's 20 centimeters. The range of our y goes from the start of the loop, y initial at 0, to y final at 20 centimeters. So when we do our integral, we have 0.80 times t times x. All those things are constant with respect to y. From 0 to 0.2 times y squared dy. The integral of y squared is y cubed over 3. That's going to be evaluated at 0.2 meters and 0. So we've got 0.80 times t times x, x was 20 centimeters, times y cubed, 0.20 meters cubed over 3, minus our term with y equals 0, that's just 0. So there's our magnetic flux. Oh dear, I didn't write down the value for that. Okay, we'll just leave that as is. So now our induced potential is minus d phi dt. So we're going to take the time derivative, 0.80 times 0.20 to the power of 4 over 3 times t. The derivative of something times t is just the constant that's in front. Okay, the first thing we notice is that induced potential is going to be constant. So we were asked for a size of a current at a certain time. What we know is that the potential is constant, so we're expecting that that current is going to be constant. So we know potential is current times resistance. So our current I is going to be our potential. Divided by the resistance, which was 0.5 ohms. Gives an induced current of, we get a minus sign here, 8.5 times 10 to the minus 4 amps. Let's just stop and take check of that minus sign. The minus means that the induced current and the induced field will act in a way to oppose the magnetic field that we've created. The problem asks for the size of the current, so it just wants the magnitude of the current. So we'll finish by saying that the size or the magnitude of the current is 8.5 times 10 to the minus 4 amps. Okay, so that's a couple of examples done. I think we'll do one more example, but we'll do that in a different video.